Okay, so if you remember, for a horizontal surface, we said we have several cases. Okay, we have to know if the fluid is above or below the surface, and if we are in the case of hot or cold surface. So here, the temperature of the surface is larger than the temperature of oil. So we are in the case of a hot surface. Plus, the fluid is above the surface, okay? So if we consider the plate, the upper surface is in contact with the fluid. So the fluid is in contact of the upper part. This is why we are in the case of upper surface of hot plate. So we can use these formulas, okay? Now, to know if we use the first one or the second one, we need Rayleigh number. If Rayleigh is between 10.4 and 10.7, we use the first. If Rayleigh is between 10.7 and 10.11, we use the second. Okay, so going back to our problem, if we calculate Rayleigh number, it's around 1.8 times 10 to the power 7. So 1.8 times 10.7 is in this range. It's larger than 10 to the power 7. So we should use this relation. 0.15 Rayleigh to the power 1 over 3. Okay, so now we evaluate average Nusselt. From average Nusselt, we evaluate average coefficient. Okay, and then we can compute the value of the heat loss from oil. It's equal to, after calculation, it's 468 watt. And we say because of energy conservation, this is the power that should be supplied to our plate in order to maintain steady state conditions. Because if you want supplied, En is equal to E out, or the generated heat is equal to the one convected out. Okay? Question on this? Okay, another problem. At the end of its manufacturing process, a wafer of diameters 150 millimeters, thickness of 1 millimeter, and emissivity of 0.65 is at an initial temperature of 325 degrees and is allowed to cool in a quiescent ambient air and large surrounding, for which T infinity equals T surrounding equals 25 degrees. We need to calculate the initial rate of cooling. Okay, so in this problem, again, we look at our figure. What do we have? We have a plate, okay? And because the thickness is really small, we can neglect this area. And we consider that the areas losing heat are the upper surface and the lower surface. Yani we have top surface and bottom surface. Is Nusselt the same for both? Nusselt number?
دكتور يعني هلا بدنا ناخذ التو كيسز، نعمل كيس لفوق وكيس لتحت.
100% بدنا نعمل كيس لفوق وكيس لتحت. For the upper one we take upper top hot surface. Okay? We take top hot surface or upper hot surface. While for the one below we take bottom hot surface. Okay? So different Nusselt relations for top and bottom. Now, what they want us to calculate? They want to calculate the initial rate of cooling. Rate of cooling is variation of temperature with time. So we need to do the energy balance for this body. So we say that the derivative of energy stored with respect to time. We use first the general equations and we simplify it. Is E dot N minus E dot out plus E dot generation. Now we simplify. No generation, no E dot N. So these two will cancel out. We just have then that the variation of energy with time, which is equal to rho times volume times Cp times derivative of temperature with respect to time, as we did before, okay, is equal, like in the first problem, is equal Q minus because we are losing, okay, minus Q convection minus Q radiation. And now for the convection, as we said, we should divide it into two parts. And to evaluate the convection loss, we need to consider H top A delta T plus H bottom A delta T. But because delta T is the same, area is the same of top and bottom, we can consider then to take it in factor. So we need to evaluate H bar top, H bar bottom, multiply them by area delta T. Now for radiation, top and bottom will lose heat by radiation, and it's 2A. 2A, which is pi d square over 4 times 2, times epsilon sigma, T to the power 4 minus T surrounding to the power 4. Now, the only remaining part is to evaluate H bar top and H bar bottom. So average values at top and bottom. So first, okay, since the fluid is air, we need to go to the table of air at film temperature, which is T surrounding plus T initial over 2. We get the value of the temperature. It's 448 Kelvin. And at this temperature, we'll evaluate all properties. Of course, here we might need interpolation if you don't have the value exactly. We go to the table of air. So we need to interpolate between 440 and 450. We do interpolation, we get all values needed, okay? And then we say, let us consider the formulas to use, okay? So we go to horizontal surface. For the top surface, we are in this case, upper surface of hot plate. And for bottom surface, we are in this case, lower surface of hot plate, okay? So for the lower surface, we don't have a choice. We have only this relation. So Rayleigh should be in this range and Prandtl should be larger than 0.7. In case it's not, I should provide you with other formulas, okay? Now, you just have to decide between these two from Rayleigh value. So let us calculate Rayleigh value. Rayleigh will be the same for top and bottom. Why? Because the characteristic length is the same. And all properties of air at film temperatures are the same. So there is one Rayleigh number, but two Nusselt, okay? So if I evaluate Rayleigh number, Rayleigh number is equal to G beta T initial minus T infinity times L cube over alpha mu. It's 2.3 times 10 to the power 5. Okay, and as we said, the characteristic length for a horizontal surface is area of the surface over the perimeter. Since here we have a circular area, so we replace area of surface by pi d square over 4, and we replace the perimeter by pi d. So the characteristic length for a horizontal circle is d over 4. Okay, and now all we have to do is to replace in Rayleigh. Rayleigh is the same for top and bottom because same characteristic length, same properties of air. So I calculate Rayleigh number. Okay, so Rayleigh is 2.3 times 10.5. If I go back to my formula sheet, 10.5 is in this range between 10.4 and 10.7. Look, Prandtl number here should be larger than 0.7. In their calculation, Prandtl is 0.69. So it's fine, yani you can use this formula, okay? Because here they said larger or equal nearly to 0.7. So if you are very close, it's fine, okay?
دكتور يعني هما نرجع نعمل calculation لبرنتال number.
هون بدنا لا مش calculation، هو من التيبل. التيبل اعطتك parental 0.69 which is very close to 0.7، يعني you can use this relation. اوكي.
اه من التيبل، اوكي.
من التيبل. التيبل بتعطيك كل هول الكاركترستكس. اوكي. واصلا فيها ما تعطيك التيبل، لانه شو البرنتال ميو اوفر الفا. يعني انت بس تلاقي ميو الفا ديفايد ميو باي الفا يو جيت برنتال. اوكي.
اوكي.
Okay. So now, if for the upper surface of hot plate, what should I use? I should use Nusselt average equal 0.54 Rayleigh to the power 1 over 4. While for the lower surface, I should use 0.52 times Rayleigh to the power 1 over 5. Okay. So if I replace in these formulas, I can find H top and H bottom. Okay, and I can calculate the total value of my loss now. I replace in my equation. I add convection from top, convection from bottom, and radiation. Okay. Any question on this?
نو.
Okay. So this is the chapter of free convection. As you can see, it's a really simple chapter. The whole idea is that I should learn how to find H bar from my empirical relations. Okay, depending on the geometry of my surface, the type of fluid that I have, this will affect the Rayleigh and H bar values. Okay.
اوكي.
Doctor, I have a
Yes.
question
Yes, Tal.
for chapter 3.
Yeah.
Like, the problem 5.
Yes.
Okay.
يلا
What's
let
your
me let me open it. Chapter 3 problems. Problem 5.
yes.
Yes. Okay, tell me. What was your problem in the area?
بال شو اسمه تحت وقت كنا عم نعمل
بالresistance. Okay. Look, into in the chapter of chapter 3, I gave you for a complete sphere the formula of resistance. For a complete sphere, the resistance is of conduction is 1 over 4 pi k times, يعني if you have between two radius R1 and R2, okay, for a spherical shape, you multiply by 1 over R1 minus 1 over R2, okay?
okay.
But this is if you have a complete area, okay? For the eye, for the eye in the problem, you have a partial area. They told you that the area corresponds to 1 over 3 of the total area. And you know that the resistance is inversely proportional to the area, okay? Because you know that what is Q conduction?
Minus
It's
KA.
K times A times dt by dr, okay? So higher the area, larger the area, larger the heat flux. And the resistance is inversely proportional to the heat rate, okay? Since the resistance is inversely proportional to the heat rate, then it's inversely proportional to the area. So if you divide the area by 3, what will happen to the to Q when you divide area by 3? Q will be divided by 3, while resistance will be multiplied by 3. Because resistance is inversely proportional to the area, inversely proportional to Q.
Okay.
Okay, that's
So,
why they used the same expression, but they multiplied by 3. Because now you are restricting your heat to go through a smaller area. So the resistance will increase.
اوكي. وعندي بس سؤال بعد الشابتر شو اسمه بروبلم 6 تحت دغري.
Yes,
آه،
problem 6.
ما
Yes.
فهمت كثير انه انا مثلا انا اعمل انتجريشن وكيف كنا هذا ولا الباوندري كونديشن هول، يعني شو بعدني ضايع.
Okay. Look, whenever whenever you have a problem with heat generation, in the part where you have heat generation, you cannot use thermal circuit. Okay? You cannot use resistances in this part. Okay? Why? Because you have variation of the conduction rate through your material. So in this material, to compute temperature variation, you need to go back to the differential equation and integrate it 2 times. Okay? While for material A and material C, no generation. Yani, if I tell you what is happening in material A, you say, if I know T1, okay, first I have a resistance to conduction inside material A until reaching here, for example, T surface A, T surface 1, okay, and here I have resistance to convection. So I can draw a thermal circuit from this point to the outer environment. Between T1, from T1 to T infinity, you have the heat flux like this, and you have the heat rate like this, and you have two resistances. If you don't know the area, you can work with heat flux, Q second. So you have here resistance R second, which is L over K. And here you have resistance to convection, 1 over H, until reaching T infinity, okay? So you can evaluate Q second 1 from the thermal circuit. You can also evaluate Q second 2 from thermal circuit after this point. Yani you can draw here from T2, okay? I can consider, I have first L of material C over K. Sorry, 1 second. Do you see the screen again?
Yes.
Okay, so you have LC over KC, and here it was LA over KA, okay? And you have until T infinity, you have 1 over H, okay? So you can draw thermal circuits of resistances in material A and material C, but not in material B. But how to connect the ideas? Q second 1 and Q second 2 are coming from which material? From
من
material B, صح? Okay. So what is happening is that material B is evacuating heat from two sides. One part, it's evacuating one part to material A. So this is what we call the Q second 1. And it's evacuating one part to material 2, which is Q second 2. Okay. But how to find how to relate Q second 1 and Q second 2? I should look at material B. For material B, I can take the whole material and apply the energy equation. I have generation in material B. So what is, and I have steady state, yani no E dot storage, E dot stored is 0. No E dot N, I just have E dot out. So what can I say? I can say that for material B, E dot generated in B is equal to total E dot out. Okay, and what is total E dot out? E dot out total is equal to Q second 1 times area of the wall plus Q second 2 times area of the wall. Okay. Now, what about the generation? You have how to calculate generation? Q dot B times volume. So it's equal to Q dot B times volume. And what is the volume of BVB? It's 2 times the length times the area, okay? 2LB times area. Because 2LB is the width of wall B. So Q dot B times 2LB times A. So A will cancel out because it's figuring out in all terms. So what can you say? I know Q dot B. Q dot B is given times 2LB, which is given, is equal to Q second 1 plus Q second 2. And I can express Q second 1 function of T1 minus T infinity and Q second 2 function of T2 minus T infinity. So I find my only unknown by writing that Q dot B times 2LB equals to Q second 1 plus Q second 2. And I replace Q second 1 and Q second 2 by their expressions. Here, what was the unknown? You have two unknowns in this problem. You have Q dot B to determine. So first you get Q dot B from this equation. Because you know all temperatures, T1, T2 are given, and T infinity is given. Okay, so you can calculate from this thermal circuit, you can calculate Q second 2. Q second 2 is Q second 1 is T1 minus T infinity over sum of resistances. You get Q second 1. To get Q second 2, you use the second circuit. Q second 2 is T2 minus T infinity over some resistances. Once you get Q second 1 and Q second 2, you replace in the energy balance of material B, you get then the generation rate Q dot B. Okay, the volumetric heat generation. Once you get Q dot B, to find the conductivity of material B, you need to consider equation, okay, of temperature variation in B. Why? Because how to calculate conductivity? Conductivity is related to conduction flux. So you need to know the conduction flux in material B. To know conduction flux in material B, but what is by definition Q conduction? It's minus K dt by dx. Minus KB times dt by dx in B. And Q conduction in B is not constant. It's varying with position because of generation. So you need to know what is the profile of temperature, T function of X, in order to evaluate dt by dx. Okay, so that's why you need to go back to differential equation. So now you say for material B, what do I have? I have steady state with generation. And for steady state with generation, if I integrate it twice, I get the following relation. Tx is minus q dot over 2kx squared plus c1x plus c2. Okay? Now, you need to determine c1 and c2. To find c1 and c2, you need two boundary conditions. What are your conditions here? You know the extreme temperatures. You know at x equal, if you take the origin at the middle of the wall, okay? At x equal plus LB, you have T2. And at x equal minus LB, you have T1. So if you replace these two boundary conditions at x equal plus L, T equal T2, at x equal minus L, T equals T1, you get two equations, two unknowns. You can solve for C1 and C2. And once you have your C1, C2, okay, then you can calculate the temperature gradient at any position. Okay, you can say that I can use now that the heat flux leaving material B, okay, is equal to what? Is equal to Q second 2, okay, and equal at the same time to minus KB times dt by dx at x equal L. Okay, now you can evaluate dt by dx at x equal L because you have the profile of temperature. If you derive with respect to time, what do you get? You get this. You get that Q second is minus KB times minus Q dot over KBX plus C1. Okay, so now if you replace C1 by its value and you replace X by LB, you say that this is equal to Q second 2 The only unknown in this equation is KB. So you can calculate the conductivity in material B. You could use this condition, or you could use the condition at the other surface, at minus L. At minus L, what is Q second conduction? It's a Q1. And actually, it's minus Q second 1. You know why it's minus? Because Q second 1 is evaluated in direction towards left, while here T is function of X is positive to the right. Okay, since X is positive to the right, then when you do minus K dt by dx, you evaluate your flux based on positive direction to the right, while your Q second 1 is in the opposite way. This is why they put here minus Q second 1. Okay, so if you use this condition or the other one, you'll get exactly the same result, and you can solve for your conductivity KB. Clear? If anything is not
Okay.
clear, I can repeat.
انا مش بس انا بس عايز ضايع بال مثلا كيو بي اوفر 2 كي بي انه وين ايش هذه الاكسبريشن تبع
اوكي،
البي
من وين
او يعني
اجت هيدي الاكسبريشن؟ هيدي اجت من الكورس ماتيريال. انت رجع للكورس ماتيريال. we derive together if we have a wall with heat generation. انت رجع للايكويشن. شو الديفرنشال ايكويشن؟ second derivative of t with respect to x. لانه اول شيء it's 1D. do you have variation with y and z؟ او بس عندك variation with x؟
بس ما لا
اوكي، بس مع الاكس يعني 1D. عندك steady state يعني no variation with time، بس عندك generation. يعني الجنريشن term ما بقى فيك تشيله مثل البيور conduction. اوكي، so now take this to the other side. شو بتصير؟ بتصير second derivative of t with respect to x. انت شفت الفيديوز؟ شيء انا حطيت لكم الفيديوز لكل البروبلمز. did you
ايه انا
watch؟
حضرتهم بس
اوكي تمام. so minus q dot over k. اوكي، هلا integrate. if you integrate the first time, what do you get? dt by dx
ماينس
minus q
كيو
dot over k times x plus c1. ما هيك؟ times x plus constant 1. if you integrate another time, شو بيطلع لك؟ minus q dot over 2kx square plus c1x plus c2. هيدي هي الايكويشن.
اوكي
اوكي
يعني انا بس هيك سؤال يعني
okay.
مش الحال.
Fine.
Thank you.
Welcome. Other question? Okay, guys, thank you. Bye bye.
باي دكتور.